What the hell, man? Shall we? You got a minute? We have an exam a week from today. It'll cover everything through what we do on Wednesday. So it's going to be a pretty long exam. I mean, long. It's going to cover a lot. All of techniques of integration, along with areas between curves, along with volumes. And that's all we'll do is just through volumes. So we'll talk more about that on Wednesday. But be prepared. I'm really hoping that over the break you got caught up. If you still haven't finished homework from chapter 6, then your ship may be sinking beyond repair because there's a lot of work ahead of us still. So, anybody dive into chapter 7 at all over the break? Anyone look at 7.1 areas between curves a little bit? Just one or two? Okay. How many of you feel like chapter 6 you're good now? I mean, as far as you've done all the work. Techniques of integration. All the techniques. Infinite limits, limits at infinity. All that. L'Hopital's rule. Partial fraction. All right. La Hospital. All right. Well, in case you've forgotten what we were doing before, we started chapter 7, section 1. We were trying to find the areas between curves. And I taught you at the end of class, or at least showed you at the end of class, how to use your graphing calculator to graph these things. So we had stopped at this problem here, and then there were two more examples that I wanted to do in class, so that's where I'm going to pick up. So I'm in 7.1 right now, areas between curves. So the instructions on this problem are to find the area of the region bounded by these two curves. 4x plus y squared equals 12, and x equals y. So the first thing you have to do is draw the region. You have to know how to draw this. So shall we try by hand, or how many of you, anyone feel good with their calculator yet? I mean, yeah, I showed you how to do the parametric mode. All right, let's try this by hand. One thing that we need to try and remember from last class is that when we do these integrals, it's going to be one of two integrals. It's either going to be a dx integral. It means we're integrating with respect to x, or dy, where we're integrating with respect to y. And the difference is when we draw that, let's say we have two curves like this. When we draw the rectangle, if the rectangle is vertical, then the integral is going to be with respect to x. If our functions are functions of y instead, where we have our rectangle going horizontal, then it'll be dy. So that's kind of the main thing to get from as we start here today. So can you tell by just looking at those whether or not we're going to be dx or dy? dy, why? Why dy? Okay, if you can solve the equations for y, in other words, you get y equals a function of x, then they're vertical, and it's dx. If you can solve the equations for x, so that they're in terms of y, then they're functions of y, then it's dy. So can I solve this first equation for x? Well, can I solve it for y? Yes, but I'd have to take a square root. And then I wouldn't have a function, right? Because I'd have a plus or minus, so it would fail the vertical line test if I tried graphing it. So if I can solve for x, then I can do dy instead. So let me solve it for x. 4x equals 12 minus y squared. Divide everything by 4. 3 minus 1/4 y squared. So that's solved in terms of y, right? X is in terms of y. And then the other one, can you solve the other one for x? I know. So you have two graphs there. Now, if you were going to do the parametric on your calculator, what would your parametric be? Okay, what is it's xt1 x1t. So on your calculator, if you did like x1t, y1t, the x1t would be 3 minus 1/4 t squared, and then the y1t would be t. If you graph that on your calculator, that will graph that first one. And then what about the other one? Your x2t, y2t will be what? tt. I know it's been a while, but yes. What do you mean? Yeah, it wouldn't matter. It's going to be the diagonal. But if you're in parametric form, you can't, on the calculators, you can't combine traditional function graphing with parametric at the same time. So you have to still write that second one in parametric form. So if y is t, then x is t. All right? So if you're following along on your calculator, you probably have to adjust your window. But that's what you would get. I mean, it's something like this, hopefully. So let's talk a little bit about this. You have a parabola opening up to the left, right? And then you have your diagonal line. I think the region between them is pretty clear to see, right? And then the rectangle goes sideways. So the way I'm trying to do this with my pictures here is that trying to illustrate the rectangle always in my drawings here to show which function minus which function gives us that length. So when it's up and down, which one goes first? Like if our rectangle goes up and down, it's the top function minus the bottom function, right? But if the rectangle goes sideways, it's the right one minus the left one. So it's the parabola, which is the 3 minus 1/4 y squared, minus the diagonal, which is the y. Are there any questions on that? Yes? No? You sure? Anybody have problem doing it on their calculator? Anyone? Yes? You still, did you type it in that way yet or no? Okay, try typing that in. For this one example, I'll give you a minute if you have your calculator to try and get this. 3 minus 1/4 t squared. Everyone that has a calculator, try it. Who still needs a calculator? Do you have access to one? You don't have access to one at all? I don't want you to have to buy one. You don't have a friend that has one or something? I mean, because really, in a class like this, traditionally, you're expected to graph these by hand. So I want you to be able to, I mean, if you have a calculator, I want you to use it. But if you don't, I don't want you to have to buy it. But You can borrow it? Yeah. Yeah. What's your major? Hmm? Okay, you need to get a calculator. Yeah. Okay. Okay. Yeah. Yeah, if it was like if you were an art major, I'd be like, nah, let's just stick it out one more. I had a Cal 3 student who was just doing it for fun. So you never know. Just for fun, yeah. Yeah. She was really sharp too. Okay. Yes, you get it? Did you get it over here? Anyone else need help on their calculator? While other people are trying to graph it, what do we still need to know? I mean, we have our integral, right? It's the right function minus the left function, but we still need the c to d. We need the limits of integration, and those are our limits on our y-axis. So that's what's the y coordinate of where these two graphs intersect, right? So what do you have to do? To figure out where those two intersect, set them equal to each other. So that's, I believe, what I do here. I say I need C and D. So I solve setting the functions equal to each other. Now, notice I wrote f of y, g of y. That's because they're both in terms of y. So here's f of y, that's the function on the right. And then here's g of y, which was the function on the left. Set them equal to each other. And now it's just, what did I do? Move the y over? Uh-oh. No, I moved everything to the right. And then I just rearranged it. Multiplied everything by 4. It's a quadratic equation, so I would expect you could solve that. I'm not going to go through it all. -6 and +2 are the two solutions. So that gives you your C and D. Did you get that finally? Yes? Okay. Now, I believe your calculator has a function in it under the math menu for the graphing that allows you to find intersection points of two graphs. I know it does. I don't know if it does for parametric, but I know for function you can have two graphs and you can find their intersection points. Okay, at this point, this is where I pretty much stop. Okay, like on a test, that's what you would do, and that's you'd move on to the next problem. And then I said you'll have to take these integrals home and solve them and bring them back, right? Well, just like on the x-axis, remember A to B went left to right? On the y, it's down to up because negative to positive. So I don't know if that answers your question. The bottom one to the top one. But you're not going to have like from 2 to -6. That's right. That would be backwards. Okay. Yep. Okay, and then if you work that out, you get 64 thirds. So the area would be 64 thirds. Okay? All right, let's look at the next example. Sketch the region enclosed by these curves and find the area. So same thing. With a quick inspection, can somebody tell me what the rectangles are going to be? Are they going to be vertical or horizontal rectangles here? Vertical, because you can solve the equations for y, right? If you can solve the equations for y, then the rectangles will be dx's, which are vertical. They're already solved for y, right? So you don't even have to do any work. So it's a matter of graphing these. I know what e to the x looks like. E to the x, everyone here should know what that looks like. It goes like this. And then x e to the x, I know it's 0, it's 0. And then at 1, it's e to the 1, which is the same as e at 1. So they should probably intersect here like this. And then it's probably going to dip down and come back up because it's asymptotic and blah, who cares? And then x equals 0 looks like vertical line. Right, x is 0 is a vertical line. So it looks like the region we have is this little region in there. How many of you got that on your calculator? Those of you who have a calculator. Anyone get it yet? No? Are you trying the parametric? So how would it be parametric? X1t, Y1t. What would that be? Whoa, what the hell? Oh, I know what happened. What would X1t be? T, and then e to the t. That would do this one. And then what would X2t, Y2t be? T, T, e to the t. Now you have to type in, that you can use the, depending on your calculators, hit your exponential key, right? Raise or. Someone raise their hand when they have the graph. You have one? Okay, you got it there too? You could go to a traditional function on this, yes. Yep. All right, well, I'm going to keep moving. Here's the nice picture of it. Adjust your window. Is your window adjusted? For t, yes, negative 10, 10. That's. It doesn't show past past negative 1. Let me see. 0 to the left. Oh, because your t minimum and t max aren't set right. Oh. Your t, I went to window. If you do t min, negative 10, t max 10, and then when you graph it, now it lets t vary between negative and positive values. You said something about it's set to 2 pi, right? It's automatically 2 pi, yes, because most parametric equations involve trig functions, sine and cosine stuff. We'll see that later on this semester. Okay, so what's the top function here? The e to the x1 is the one on top, right? E to the x is on top, and then the x e to the x is on the bottom when you're looking between here and here. And so that's where this rectangle comes from right here. And there's my integral. And now we just need a and b, don't we? Need to figure out where they hit each other. Do you have a question? No? What's your window say? Hit window. What's your t min? Yeah, change it to negative 10 and 10. Okay, so we have to find out a and b. Now, do we already know any of these? We already know a, right? Just from visual inspection, x equals 0 is a. The only thing we really need is b, and b is the intersection of those two graphs, right? So I'm going to have to set those equal to each other. So when I set them equal to each other, I'm setting e to the x equal to x e to the x. You can move x e to the x to the left side. You can factor out an e to the x. You can set each of these equal to 0. E to the x can never be 0, so there's no solution here. 1 minus x is 0 at x equals 1. And that's it. So you have your a and your b now. And then, again, you would set up your integral 0 to 1 of this. That's it. That's the end of the test. But then at home, you would do all that, get this answer. So what are you thinking the challenge of these problems is going to be for you? Like drawing them, you think? The region or? The intersections? Yeah, which way it goes. Yeah. Let's go back and look at this picture. Why would I not do rectangles the other way? Like, what if I had this rectangle right here? I have a function to the right, don't I? What's the function to the left? 0. That's okay. That's okay. I have a top and a bottom. The problem is what? It changes, right? Like once I get to this point right here, right across there, now my rectangle would look like this, and now it would be, the top one would be the green function, the bottom one would be the red, wouldn't it? So I could do it that way, but it would require me setting up two integrals and adding those two answers together. So it's just harder this way. That's all. Do y'all know what I mean by changes? Yes? Okay. The C to D, the limits of integration would change. Yeah, it would be 0 to 1 and then 1 to what? Yeah, you would have to figure that out now, right? Okay, and that was it. Now, I finished up the solutions for all the even problems for 7-1, and then I just did the odd ones also. And I'm going to put those out on the web for you. All right. I'll show you, though, here. Where do we have here? Review solutions, homework solutions, 7-1 even. Here are the 7-1 even problems. So I just wanted to walk through a couple of these. Let me do. So if you have your book, grab a book. At least have one book on each table, so you can know what I'm talking about. I'm on 7-1 now. This is it's page 369. Your homework assignment is going to be 1 through 17 odd for 7.1, page 369. I'll put it on the board in a little while. 1 through 17. You see how far I went. Oh, wait. I take that back. 19. So sorry. So sorry. Is it what? Okay, so what I'd like to do right now is very quickly go through some of these even problems, all right? Just so you can see the setup on them, all right? And what challenges you might be presented with. So please look at number 6 and notice the way the problem is presented on number 6. Does everyone, who doesn't have a book? Is everyone at least able to see no book over there? They give you y equals sine x, y equals x equals pi over 2, x equals pi. So what I started doing on these homework problems is I started to point out, like I started to color code all the functions. So my y equals x was blue, my sine function was black, x equals pi over 2 was green, x equals pi was red, and then when I draw my rectangle, I have my little blue and then my black right there, and you can kind of see it's the x minus the sine. Do y'all see that, how that works? And that helps, I think, helps you set up the integral, top minus bottom, and then your limits of integration. And then from there, you go. But again, the challenge is going to be the drawing of it, right? This part is I think, the most difficult part of the whole thing. What's that? Well, you don't need to color code. This is just for you to look at and know what the hell I was doing. Yeah, you don't need to color code anything. Color pencil, fine if you want to. Okay, so let's look at this one. Number 8. Y equals sine x, y equals 2x over pi. This one was tricky because the sine functions here, 2 over pi x is a line that has a slope of 2 over pi. So it winds up being below the sine function in here. And it creates a little region. And there you have little vertical rectangles. And so you have, you figure out your top and your bottom and draw your little thing over here. And you did they give you pi over 2? No. Which one is this? X? No, they don't. So I had to find that point of intersection. I had to find it. So I'm sure, well, I didn't show any work, did I? Pardon me? X equal. That just means to the right of 0. So they said find the area of the region bounded by these two curves to the right of 0. So because to the left, there's actually a part over here too. And so they're saying don't include that. All right, let's look at the next one. I'm just going to go through these. Number 10. Hey, I just did that one in class, didn't I? Yeah, I did this one just a second ago. So I'm not going to do that one again. Number 12. So the number 12, it has two parabolas, one that opens up, one that opens down. So you can figure out, what's your top function, what's your bottom function, set up your little, f minus g, and then you have to figure out where they intersect. So you have to set the two quadratic functions equal to each other. Then move everything over, solve a quadratic, and you've got your 2 points of intersection. Does this all kind of make sense or not? I mean, okay, this one was definitely tough to graph by hand. Notice that these graphs I've done here are not by the computer anymore. I've done these by hand. This one was hard. Cosine x, like I know cosine x look like that, right? And then this function here, 2 minus cosine x, is the same as negative cosine x plus 2. So I took cosine x, made it negative, which flipped it over the x-axis, and then moved the whole thing up 2, and it created this. So I've got this, I don't know what the hell that thing looks like, but whatever it is, it was perfect. It was perfect for vertical rectangles, right? And so I have my top function minus my bottom one here. My limits of integration were given to me in the problem, 0 to 2 pi. And so I know I go from 0 to 2 pi, and then I carry out the integration. 16. So they gave me x equals y to the 4th. That's solved for x, isn't it? This one, y equals square root of 2 minus x. This one's solved for y. And then y equals 0 is the x-axis, right? So should we solve for x or for y? Yx. Well, because I did? Oh, okay. No, y then. Yeah, squaring both sides. That's right. But it's not only because it's easier. It's because if you try and solve for y, you're going to have to take the 4th root, which means you have to do plus or minus, which gives you 2 functions. By squaring both sides, you don't have 2 functions. Now, this red one right here, if I graph this red one, it is actually a parabola. It continues around, but why did I stop it? Why did I cut it off right here? Yeah, because of the y equals 0, but also because look at this. The original function was y is the square root of this, right? That means that the y can only be a positive number, can it? Like this square root can never turn out to be negative. So this graph can never come below. Yeah? So that created this region. That region was perfect for horizontal because I have a top or a right function and a left function. And then there it is. Here's my right function minus my left function. Put it into the integral. 0 to 1, where did I get 0 to 1 from? 0 would be this one, right? I'm moving here, then up. So how did I get the 1? Set them equal to each other and solved, right? And when I did that, I actually got plus or minus 1. But I know it's not negative, so. You see, so there's little subtleties in this stuff that you have to pay attention to. Any questions on that one? Is this helping by going through this like this, or? Okay, 18. That's kind of interesting. We have an absolute value function, which is a v, and then we have a parabola that's been moved down to, so it looks like that. Create a nice region. Notice the vertical rectangles are perfect there, right? These vertical rectangles. As I move through from left to right, I always have the red function on top of the green, right? Red on top of green the whole time. But I did something in here. What did I do? See, what's the antiderivative of the absolute value of x? We don't really have one. So I use symmetry here. Yeah, since this is symmetric, instead of saying, let me go from A to B, I went from 0 to 2, which is from here to here. How did I find 2? I did this right here, right? And then whatever that area is, double it, so I put a 2 in front of the integral. This is a good time to talk about absolute value equations. I had to set the two functions equal to each other, didn't I? How do you solve an absolute value equation? Absolute value of x equals something. Well, you drop the absolute value sign and you just write down the equation. And then you have to drop the absolute value sign and change the signs of everything on the other side to negative. So you wind up solving two different equations. I wind up getting two answers here and two answers here. Then I have to check each one into the original problem to see if they work. And when I did that, one of them worked here, the other one didn't. This is a green check and a red no. And this one's a green check and there's a red no down there. So by checking them, I found the two answers were 2 and negative 2. But because of symmetry, I only did the 0 to 2 instead of negative 2 to 2. When I went from 0 to 2 instead, why did I change absolute value of x just to x? See, I went from absolute. Why did I change that?
0 to 2 is going to be positive.
Because from 0 to 2, right? From 0 to 2, that diagonal line is basically y equals x, isn't it? That problem's a little tricky. Let's see if 20. Oh, 20 was pretty. Oh, this was a good problem. Like my zoom in. So I had like a parabola here. This is my 1/4 x squared. Then I had my 2x squared as the red one. Then I had this line, which I solved for y, and it's this right here. I'm trying to find the region bounded by all three, which turned out to be this yellow region here. And notice that it was not suited for vertical or horizontal rectangles, right? Neither way was better. No matter how I did it, I was going to have to break it into two regions. So I did it vertically. So notice I have a green region. I mean green, that's not green. That's yellow today. And this is like a bluish, right? So in the yellow, the top function is the red one and the bottom is the black one, right? But once you get to the blue section, the top is the blue function, the bottom is the black. And so that's going to create two little rectangles. You see that? And that means I'm going to have what below this? Two integrals. But I needed to find what? A, B, and C. A is this point, 0. That's, you can just tell. B is where these two hit. C is where these two hit. Do y'all follow that? A is 0. B is where the red one and the blue one hit. And C is where the black one and the blue one hit. That's right. It will be, but I had to find them first, so I think I found them first. So to get A, I could have just did it by looking, right? But I said A is this, right? So I set the red and the black one together equal and solved. I got 0. To find B, I set the red and blue one together. Here's red and blue. Set it equal. I got 1. And then to get C, I set the blue and the black together, and then I solved that and got 2. So there's my A, B, and C. Yes.
Plug it back in and it didn't work.
It's not in it's not in this region. Negative, it's on the other side of the x-axis, so it's not, the line isn't over there. Yeah. Or I should say it's where, go back up to the picture. It's over here. It's over here somewhere. Oh, and look at this right here. X is bigger than 0. There you go. So, and now here are my two integrals. So I went from 0 to 1. That gives me the yellow region. It was the top minus the bottom, which is this. Then from 1 to 2, that's the second little part of the picture, the blue part, and then the top and bottom. And then you work those out and you get 3/2. Okay? So your homework will be pretty much the same. Your functions will be a little different. Like I said, I did all the odd ones already. These are all the evens. I worked the odd ones the same way. I might just wait until maybe Wednesday evening or Thursday to put those out. I want you to at least try them on your own. Okay? And that does it for 7-1. All right? So here's today. Today is here. I'm going to insert a new page here real quick. So your homework for 7.1 is page 369, 1 through 19 odd. All right, 7.2, y'all ready? I'm kind of upset. I had prepared this really, really awesome demonstration using Mathematica, and then I had this issue occur in my college algebra class before this class, where I had to deal with the student issue, and I wasn't able to go home because I forgot it on my flash drive, the nice program I had to show you this animation and stuff. So I put like 3 hours into this animation. I'm not even going to be able to show it to you. You'll have to wait till next class. But I do have something to show you. So I'm kind of disappointed. All spring break. Okay, so we are going to now talk about volumes. And we're not talking about like speaker volumes. We're talking about three-dimensional physical volume, right? You have one dimension. Measurement of one dimension is length, right? 2 dimensions, you can measure areas. 3 dimensions, you talk about volumes. So we are going to, this 7.2 is volumes in what's called the method of washers. And before we can even begin, we have to remember the basic formula for the volume of a cylinder. So if you take a cylinder, right, beer can or whatever it is, in the spirit of spring break, we'll say empty beer can, and the volume of it, right, is pi r squared times h. Why does this formula make sense? What's pi r squared? That's the area of a circle, isn't it? Pi r squared is the area of a circle. Times h is just the height of the rectangle, the cylinder. So it's just like you're taking an area of a circle on the bottom and stacking them h high, and that's where you get the volume, right? Okay. Now, here's what we're going to try and do. So here's the demo, but this is like my first version of the demo. I did a lot of work to it afterward. We have this picture, right? A graph. And we were taking something like an arbitrary rectangle, right? And that was our little, what, dx was the width of it, right? How tall was it? How tall is this? Whatever the function is, right? So that's like f of x was the height, dx was the width, and then if we made infinitely many in there and added them up, and that was the integral, and then we had the area underneath, right? That was the area. So the idea of getting the area under this was figure out the area of that rectangle, add them up forever, integral, right? So instead, and I have to unfortunately spin this for a second. You ready? We're about to get three-dimensional. Okay. Okay, y'all see this? Ready? Okay, I'm going to pop it out of two-dimensional space into three-dimensional space. Okay? I'm going to take it. I'm going to take that one sliver and I'm going to wrap it around the x-axis. Okay? See that? I wrapped it around the x-axis. And so now I've got, instead of having a little rectangle with an area, I actually have a very, very flattened out beer can that has a volume, doesn't it? And if I take that and I add them all up, I will get the volume of the solid that's created by revolving that function around the x-axis, which would almost look like a football, wouldn't it? Yes? Okay. So here's, sorry, like I said, I was prepared, but I forgot something. Revolve. Mathematica has some built-in stuff, so I can use theirs real quick. Theirs is going to be going to look a little odd, but let me try this. Let me pop this in here. That was just sine t from 0 to pi. Uh-oh. I really want to show you the football, but I'm having some issues here. See, this took sine, but it rotated around the wrong axis. Do y'all see that this is the sine function rotated around the y-axis? Or no? Like, take that picture I had before, and instead of going this way, go this way with it. Like, take that and swing it around, and what would you get? You would get what I just had, right? Right there? That's that? Yes? All right, well, I have a backup plan. Y'all just hang tight. Can y'all see it, though, without me giving you a picture? Or there's a program called WinPlot. It's free. Three-dimensional graph. Wait a minute. Who's taking pictures? Is that someone taking pictures? Oh. I was like, it's not that interesting. 0 to pi. There we go. Okay, so that's the graph, right? Let me see if I can't get this to work. I want to rotate. Shit. Yeah, it's not happening. I think you'll have to just stand by for next class. I apologize. Y'all can go. Let's call it a day.
You probably use Xref.
Yeah, I don't have it on this computer. It'll do it. I just I don't want to sit here and start coding all this stuff up in the middle of class. You know what I'm saying? I just want to like. Okay, let's get back to work. All right. That's the idea of what we want to do today. Take this and spin that sucker around the x-axis and figure out the volume. All right. So here we go. If I take that thing, that rectangle, and I spin it around, I create this shape, right? And that's a washer. Now, normally a washer you would imagine having like a hole in the center of it. It's a washer that's standing up. That's a solid washer, right? Solid washer. And how wide is it? How wide is this washer? dx, because isn't it the same as the width of the yellow rectangle, right? This width right here was dx, and since I revolved it, that would also be dx. Okay, tell me about from the center of this out to the edge, which would be the radius, wouldn't it? What is the radius of that? F of x. That is the height of the function, rotated around, isn't it? You take that height, f of x, you rotate it around, that's the radius of the washer, isn't it? And my x-axis goes through the center here like this. X-axis. Everyone see that? What's the volume of that washer then? Volume is pi r squared h, isn't it? But what's the radius for us? F of x, so it's pi in brackets f of x squared. And then what's the height of this? It's the height, remember this is a cylinder, this is a beer can laying on its side, right? So the height is actually the dx, isn't it? Isn't it? dx. Well, go back up to this picture right here. Remember that picture of the height? If I draw my can like this instead, right? Then my radius is right here, right? And my height is this distance right here, right? That's my height. That's my height. So on our picture, it's that laying on its side. The dx is the height. Do you see that? Okay. So everything matches up in the formula here. We've got pi is pi, radius is f of x, there's my squared, and my height is dx. And that would give me the volume of that one little washer, right? So how do I find the volume of the entire function rotated around the x-axis? Take the integral, right? Integrate. So if I want the whole thing, the total volume would be the integral from where to where, though? A to B of, what are you adding up? What are the things you're adding up? All the little washers, right? So what's the formula for the washer? Pi f of x squared dx. So in general, if you have a function that you ever want to rotate around the x-axis and find the volume of that solid, it's the integral from a to b of pi times the function squared dx. That's it. That makes sense? So that's it right there. That's kind of our big formula. So we'll do an example. Fine. Let me see. Again, y'all have the books with you, right? So let's try one of these. I haven't done any problems from 7-2 yet, so this ought to be fun. I'm going to do number 2. This is page 378, number 2. So it gives me y equals 1 minus x squared, y equals 0. And it tells me about the x-axis. So it would like the instructions say, find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, in typical disc or washer. All right, here comes my drawing. So I have to know what that looks like first, right? Let me do it in 2 dimensions first. 1 minus x squared looks like a parabola. It opens down, intersects at 1 and -1, right? And then y equals 0 is the x-axis. So we're talking about the region in here, enclosed by those two. And we're not finding that area, right? We want to rotate that region around the x-axis. So I can imagine coming in here with a rectangle, a vertical rectangle, right? Vertical rectangle, not horizontal, vertical rectangle. That rectangle, when I spin it around the x-axis, creates my solid washer. What's the radius of this washer? So that, yeah, it's the function, which for us is 1 minus x squared, right? And then it's dx wide. And my integral is going to now be ready to be set up, isn't it? What's the integral? Where to where? -1 to 1, because you want both sides. You want the whole thing over. -1 to 1 of pi times the function 1 minus x squared, but then squared dx. Which becomes pi integral -1 to 1. If I were being asked to integrate that, here's how I would do it. 1 minus 2x squared plus x to the 4th dx. What did I do? I pulled the pi out, right? And then I actually just expanded 1 minus x squared times itself, and then did like a FOIL and collected like terms. And that way I could do term by term integration. And then whatever that answer is. Okay? And that represents the volume of the solid generated by rotating that region around the x-axis. And what would it look like? Like an egg, right? I mean, it's not a ball, it's not a sphere, but it's kind of close to one, right? Okay. It's hard to draw these things three-dimensionally. I mean, you could try it. I mean, it might look something like this. I mean, that's your three-dimensional. I don't know, man. It's tough. It's hard to draw 3 dimensions on 2.
Since y equals 0, does that mean there's just a rectangle on one side and a rectangle on the other side? Or does that not make sense?
Y equals 0 is the x-axis. It's that purple on the bottom.
Oh, okay.
Yeah, I think your x equals 0? Yeah, okay. All right, how is that? That okay? Questions? Yes. And double it? You could here because it's symmetric. In general, though, no. But if it's symmetric, if you know it is, then you can do that. Yep. Okay, let's look at something a little more general, okay? How about this? How about we have a function like this, and then we have another function that does something like this, and we want to rotate the region bounded by those two around the x-axis. So notice I'm going to put here, next to my x-axis, I'm going to draw a little curved arrow. See a little curved arrow? That's going to mean I'm rotating around the x-axis. Because as you'll see later, we're going to do some things around the y-axis. So instead of just a single function wrapped around, I want to know the volume of just that region wrapped around. So let me draw a rectangle first. My rectangle no longer goes all the way to the ground, does it? So there's my rectangle. If I wrap that around the x-axis, what's it going to look like? A mushroom? What? A washer. With a hole in it, right? So now it's kind of a true washer now. And I'm color coding this too because isn't the hollow part because the red cuts it off? Like if it was just the blue function wrapped around, it would be a solid washer, wouldn't it? But you're cutting out the red part, right? Yay or nay? Where's my axis of rotation? Okay, so before I do this, before we try and get a formula for this, let me see if we can come to an agreement on this. I'm going to draw two pictures side by side. This would be just the blue washer. I'm going to start getting real sketchy with these. That's just the blue wrapped around, isn't it? If I said just wrap the red around, it would be this, wouldn't it? So if you want the washer that has the red taken out of the blue, right? Cut that out. Then you want the volume of that minus the volume of that, don't you? So shouldn't the volume of, whoa, oh, I lost my stylus. There it comes. I think I'm picking up someone's Bluetooth. So this guy up here, this one right here with the hollow, would be this volume of the blue, right, minus the volume of the red, which means that what's the volume of the blue? We already know the volume of the blue would be pi times its radius squared, right? Now, I need to label some of these functions. How about we label the blue one f, and we label the red one g? How about that? And now I can talk about them in the integral. The volume of the blue one then would be pi f of x squared, right? Dx. And then the volume of the red one would be minus pi times the g of x squared dx. And so at this point, you could pull a pi out of both of those, right? Right? And then you could just put f of x squared minus g of x squared dx. I just pulled the pi out, and then they both have a dx in them, right? So I put the dx at the end. So if you distribute pi and dx through the parentheses, you get back the previous line. And that would give us the volume of that one washer, wouldn't it? Now if we want to add them up and get the whole thing, integral, where to where? Well, we never labeled it, but it would be A and B, which we would probably have to find out by doing what? Setting the two functions equal to each other. So we'd have something like final version here, integral A to B pi, which you could pull out of the integral, f of x squared minus g of x squared dx. And that would be the volume of the solid generated by rotating the region bounded by those two curves around the x-axis. Why am I putting the f of x and g of x in brackets?
That way you know it's not just a.
Yeah, it's all about notation. Like if I write, come on, if I write f of x squared, that can be confused. Like, are you squaring the x? What? Technically, though, you could write it like this. That's also proper. This is okay. This is not. So proper notation for squaring a function is putting a squared there. What does this mean? Because that's another notation. Anyone know what that means?
Don't you square both?
That's second derivative. So because remember, derivatives were like f prime, f double prime, f triple prime. What if I want to take the eighth derivative? How do I say it? I don't put an 8 here because that means raise f to the eighth power. So to distinguish between raising to a power and derivatives, we put it in parentheses. That's just bonus coverage. Okay. All right, we have 40 minutes. Now, shall we do an example of one of these? Okay, let's try and see if we can figure one of these out. I'm just going to make one up. Okay, as an example, let's do well, maybe I'm not going to make one up. I'm going to do number 6. Y equals 1/4 x squared. Y equals 5 minus x squared. Let's rotate this about the x-axis. So we want the region enclosed by those two functions wrapped around the x-axis. So we have to draw them first. A blue one, let's see, 1/4 x squared. I'll make that my blue one. That just looks like a parabola, opens up. This. 5 minus x squared. Was I using red? Yeah, red. That'll be my red one. That's a parabola opening down, moved up 5. So it's going to look like this. I think the region enclosed by both of those is pretty obvious, isn't it? It's this region in here. My typical rectangle in there is going to be a vertical rectangle. And when I spin that around the x-axis, it will create a washer, won't it? It'll be it will have a hole in it. Will it?
It'll be touching at the apex of the bottom from the blue function.
Yeah, this is a weird looking solid.
It's like a donut that expands and squishes out.
Yeah, I mean it's a donut that touches itself on the inside, pretty much. Man, I wish I had the other program because I could just type in a function and it would do it, and I'll have it next time. Okay, sorry. So I will have a little bit of a hole in here, won't I? At some points. You know, it's in the middle it won't, but where I drew the rectangle, it will, won't it?
Yes.
Yes? Okay. Do we have an upper function and a lower function? Yes? Okay, so what is the formula that we just generated? Integral from a to b of pi, then f of x squared minus g of x squared dx. So we need the a to b, don't we? So how are we going to find out the a and b? The a.
Equal amount to each other?
Yeah, set them equal to each other. So let's find a and b. I'll just write it down what it is, and then I'll leave it to you to set it up. 1/4 x squared equals 5 minus x squared. And what did you get? Okay, this dot dot dot, you get -2 and +2. You can just check by inspection too. Plug in 2, it works. Plug in -2. Everyone understand you would have to do that on your own, like algebraically, or however you're using a calculator. So my integral becomes integral -2 to +2 of pi times the first function squared. What's the first function? Now that's going to be the one on top. So which one's on top? It's the red one, right? So 5 minus x squared. But then squared, right? 5 minus x squared squared minus now the bottom function, which is the blue one, 1/4 x squared squared and then dx. And then you expand it all out and collect like terms and you're ready to go.
So pretty much like on the test, you would have us get this far, and then we would take it home.
That's right. I would want to see that for sure.
Yeah.
I really don't even care about you like spanning it out.
Yeah.
That you can do at home. That's just like busy work. My main thing is, can you draw it out, visualize what's happening, show me that. You know, what I don't want on the test is just the integral. You know, I'd like to see your graph. I'd like you to show me, you know, the rectangle in there. You know, that way I know if you went vertical or horizontal. You know, and then once the integral's there, you're ready. Move on. What we want to get to eventually with things like this is, let's say that this thing, this solid, right, has a varying density. In other words, maybe it's more dense, there's more mass to it towards the edges, and on the inside it gets less dense or the other way around. And then you can actually figure out centers of mass, moments of inertia. These are all physics things. But they're all integrals, and it's all about setting them up. Once you set them up, you know, calculating them is somewhat trivial. All right, well, if we can rotate around the x-axis, we can rotate around the y-axis, right? So let's do it around the y. And let's do a general picture around the y. So I'm going to start this by saying y-axis rotation. So the first thing we need is to be able to do an integral that's a dy instead of a dx. So our two functions are going to need to be functions of y instead of x. So my region that I want to rotate is this. And my rectangle would be horizontal instead of vertical. And let me label the blue one. Let's call this one f of y. And the red one on the inside, we'll call it g of y. Everyone see this is the same thing, just sideways now? What are our limits of integration going to be? We still go c to d. But now when we revolve, right, our washer would look like this instead. It would go this way. It would be hollowed out in the center. Like that, right? And so, pi r squared times h is the same formula. So we have dy's instead of dx's, and we still have the top one and the bottom one. So what would we have? See if I don't know. I don't want to push too far, but at the same time, I don't want to like baby you through this. What would this integral be for the total volume, rotating that around the y-axis? C to d, pi, f of y squared. Good. Good. That's it. So it's the same thing, the other direction. Okay, let's look at number. That one's kind of boring. All right, we'll look at number 8. So let's say we have. Oh, wait a minute. Hold on. Yeah, we can do it. We can try this. Y equals 1/4 x squared. X equals 2. Y equals 0. About the y-axis. So we're becoming somewhat pro at graphing here. Not at all, huh? Y equals 1/4 x squared is that parabola again. X equals 2 is a vertical line, isn't it? Y equals 0 is the x-axis, right? So my region is right in here. Yes? That's x equals 2, y equals 0 in that parabola. That's the region bounded by all three, isn't it? But I want to go around the y-axis. So I'm going to put my little arrow here showing rotation around y-axis instead of x. See how I put that down on the bottom? I'm going this way. If I go this way, then I need to have my rectangle going this way like this. So I'm going to blow that rectangle up over here just so we can see it. On the top of that rectangle, I have the red function. On the bottom, I have the blue, don't I? Like this. But we need them to be in terms of what? Like, solve them for what variable? If we're going to do sideways rectangle. We need to solve for x. So let's look at the blue one here. The blue one, if I solve that for x, then I multiply both sides by 4, and then take the square root, right? Which gives you plus or minus root 4y equals x. Plus or minus 2 root y. Plus or minus 2 root y equals x. Now I can't use them both, right? Which one is it? Why is it the plus, not the minus? When you're on this blue part of the parabola right here, right? When you're on the blue, what's the x values over here? Positive, right? And see, your x is whatever this is. So if you put negative there, then it's going to be negative values. You don't want that. That would give you this side. So you do the positive 2 root y. So that means I'm going to put it as, what is it, the f or the g? This one. Is it going to be the right one or left one? The blue one. It's going to be the one on the left, right? So that's my g function. The f is the one on the right. So I'm going to put it here like this. G of y equals 2 root y. Okay, that's my g. What about the red one, though? What's that one? Can you solve that one for x? Yeah. X is what? X is 2. So it's a constant function, isn't it? Do we have our limits of integration? Do we have where they hit each other? So we have to hit here and then here, right? 0 to where? That's what we got to figure out, right? So you set the two equal to each other. I'll do that over here. To find C and D, C is equal to 0. I got that. To find D, I set 2 root y equal to the other function, which was 2. Y'all see what I'm doing? I'm setting the g equal to the f function. I forgot to label that one f. F of y equals 2. So when you set them equal, divide both sides by 2, you get root y equals 1. Square both sides, y equals 1. So that's a 1 up there. So we're ready. Integral goes from 0 to 1, pi, then in brackets here, our f function, which was 2 squared, minus our g function, which was 2 root y squared dy. And that's it. That would be pretty easy to integrate, right? Because that's just 4 minus 4y. 4 minus 4y. Wonderful. Okay, let's do a quick little show of hands here. How many of you feel like you're catching on to this, at least understand from the picture? Okay, good. That means too many people are understanding. I need to make this a little harder then. What we want to do now is we want to have a generalization, okay, as general as we can get. So far, we've been rotating around the x-axis and we've been rotating around the y-axis, right? But there's nothing that says we can't rotate around any line. And so we want a more general picture. So here's going to be our first rotation about any horizontal line. Horizontal lines are defined like y equals a constant, right? Horizontal lines, y equals some number. So I'm going to say y equals, and I'm going to call it k. I'm not going to use c because c was like our integrals from c to d. I don't want to use c. So I'm going to use y equals k. So here's my picture. I've got an x and y axes here. And now let me start with a line, a horizontal line. So I'm going to come in here with a dotted green line, and I'm just going to throw it wherever I want. Here's my dotted green line. That's y equals k, right? And I want to rotate around that line instead of around the x-axis. And then I'm going to come in here and I'm going to draw two functions like I did before. And if you wrap that region around that line, right, it's almost like wrapping it around the x-axis, isn't it? But it's not the x-axis. So what's changed? I mean, what's the difference between wrapping that around the x-axis versus the line y equals k as I have it drawn? It's going to be a bigger gap, right? A bigger inside of that washer. So how do we account for that? Yeah, it changes our radius. Let me draw my rectangle in here first. Here's my rectangle. That's still the piece that's getting wrapped, right? But as before, remember before it was just, okay, imagine the blue one around the x-axis, that was just f of x, right? And then the red one was just g of x. We need to account for this, so we need to somehow add that to the radius change, right? To the total radius. Well, I'm not going to give you a general formula like that because k could be positive or negative. Instead, I want you to think of it visually. I want you to look at it as an outer distance and an inner distance. Okay? Outer distance and inner distance. So if I'm standing here, I'm actually physically standing on this line. Here's my head. My eyes are pointed that way. How far away is the blue up there? What's the distance from me to there? It's going to be the distance from the x-axis to there, which is the function, right? Plus this distance, which is whatever k is, but be careful because if k is -2, it's not -2, it's what? +2. It's that distance. So you look at it more like an absolute value almost, okay, in this case. So I'm going to draw it like this. I'm going to say, guess I'll do it in blue. The distance from here all the way down is what I'm going to call the outer, I'm going to call the outer radius, right? The outer radius. And then the other one is going to be the inner. Is outer 1t? It is, right? Looks weird? Yeah. So I also have my A and B, don't I? I'm just going to write A, and then over here I'm going to write my B. So the formula should look like this. Integral A to B pi times outer squared minus inner squared. And in this case, D what? X, right? See, that's more general, but you would have to be able to look at this and see what's going on. Just remember, your outer radius is the total distance from your axis of rotation to the outer ring. And then the inner one is from where you are to that red part. Okay? So let's see if you got that. Let's do an example. Let's do number 10, but I'm going to modify it. Let's take y equals e to the negative x, y equals 1, x equals 2, and I want to rotate that about y equals -3. What I'm known for doing on tests like this is I give you a region like this, and I ask you to rotate it around 3 different lines. So I say part A, rotate around the x-axis. Part B, y equals 2. Part C. And all you do is create the formulas for each one, show that there's a difference, and you're done. Okay? All right, let's try and draw this. E to the negative x. What does e to the negative x look like? 1 over e to the x. Good. What does that look like? Ask your calculator, see what it says. It's e to the x reflected over the y-axis. So this is 1 right there. Does your calculator concur with me? Yes? Okay. Then y equals 1. Y equals 1 is horizontal line, isn't it? Like this. And x equals 2 is a vertical line like this. Everyone see the region? Nice little rectangle in here like this. Oh, what have I not drawn yet? Very important here. Axis of rotation. Yeah, I'm going to try and... there's more colors here. Let me see what else I can do. Let's do that. Oh, wait. Okay, y equals what? Negative 3? 1, 2, 3. That color looks like red anyway, doesn't it? Negative 3. But that's okay. Now, to let you know that's my axis of rotation, I'm going to draw that little kind of circle around like that for my axis. This is the most critical part of the whole problem now. Determining your outer and inner radius. So let's try with the outer. That would be the total distance from the top of that rectangle all the way down to that line. What is that? 4, right? It's the red line, which is constant, right? 1 plus 3. So it's a total distance of 4. You don't add 1 and negative 3 and get negative 2. It's the total distance. Does that make sense? Okay. And now, so the outer is 4. And then what about the inner radius? I'm going to have to do it from here. Let me see. Inner is the e to the what? Negative x, then plus 3. Plus 3. Or minus a negative 3. But however you see it, you need to count that. It's a distance, not the value itself. Okay? All right. So that's it now. We need the limits of integration, though. Do we have limits of integration? Where does it go from? 0 to 2? So isn't that it? I mean, we have everything for the integral. Integral 0 to 2 of pi. Then the inner function, or wait, outer 1 squared. So 4 squared. Because my region here, right, this region in here, the x value starts at 0 there and ends over here at 2. You see what I'm saying? Okay, so that's my outer squared minus what? Inner squared, e to the negative x plus 3 squared dx. Not bad? That's okay?
It's easy.
It's easy. Okay.
Fine. It's fine.
It's all right?
It's alright.
Okay. Let's try the same problem, but I want to do something different. Okay? I want to take this same exact problem and I want to rotate it around y equals 3 instead of negative 3. So y equals e to the negative x, y equals 1, x equals, wait, they didn't give you x equals 2, did they? Yeah, they did. X equals 2, about y equals 3. So our picture's exactly the same, isn't it? There's no difference? I mean, except for the axis of rotation. Our picture does the same thing. X equals 2. I've done that in y equals 1. Okay, now here comes my y equals 3. Please pay attention to this. This is really, really important. This is y equals 3, isn't it? Yes? Okay. Everyone's okay with my region, right? My region's this same little bluish area here, right? I want to rotate that around. My rectangle inside there looks like this. All right, there's my rectangle. But what's the outer? See, you have to remember, you're standing right here, right? My purple little dot there. You're standing there looking out at the rectangle, right? So if I'm standing here looking out at the rectangle, the outer one is the distance from me to that blue, isn't it? And the inner one is the distance from me to the red. Now, this you have to be careful with this. What's the distance from the purple to the x-axis? 3, right? And then what happens to get you back to here? What do you have to take away from that? Whatever the value of the function is, right? So isn't the distance from here to this tip 3 take away e to the negative x? So as I move over, like move over and do a different rectangle here. See, it's changed now, hasn't it? So now I'm standing here instead. So now as I move over, what's happened? Instead of being 3 take away that much, it's 3 take away even more. And the thing that's creating the more is the e to the x function right there. Does that kind of make sense? I'm always hesitant to show it this way because books don't ever do it this way. But that's the way it made most sense to me as a student. So the outer, let me do my outer here. Okay, the outer, and I'll do the in, is the distance from here to here. And I'll just label what they are below this. The outer was what? 3 minus e to the negative x. And then what's the inner? It's constant, right? It's always 2. And so do we have the limits of integration? Same as last time, 0 to 2. Integral 0 to 2. Outer squared minus inner squared dx. What we will never do in this class is we will never rotate around a line that cuts through our region. Okay? Our region will always not, our region and our line of rotation, or axis of rotation, will never intersect each other. Because, I mean, that just kind of, it's kind of weird if you think about it, what's happening there. You kind of like get double, well, think about it yourself. It's like double, it goes through the same region twice. It's kind of weird. So we won't do that. We also will never do non-horizontal lines or non-vertical. So we won't do slanted lines. It can be done, but we won't do them.
So we won't do like rotate around like f of x equals 2x.
No. Do you want to?
Well, I'm just asking
No.
because you want to. I've done it before. That's why.
Yeah. Well, there's ways to do it. There's ways to do it
Yeah.
where you take a region, you rotate it around a line that's non-vertical or horizontal, but what's that?
Around that function.
Yeah, around a function. You can do it, but there's more efficient ways of doing it beyond this class. So you can really like do it and be hard, and it can be really hard here, but later on you can do it real quickly, because all you do is you just take everything and you rotate it, and then it just becomes a problem of going over the axis. So yeah, you have to be able to somehow know something about it. So, but we won't touch it. Yes. Because if you're standing there at the purple again, right? If you're standing on the purple and you're trying to measure the distance from here to here, to the red, you know the distance from here all the way to here is 3, right? And what's the distance from here to here? 1. So the distance from here to here has to be 2. Don't look at it as taking 3 and subtracting 1, or, taking 3 and subtract. Try and look at it like, seriously, like you're standing there and you're trying to measure how far. Like, I know from me to the x-axis is 3, and I know from the x-axis to that other red one is 1, so that means from me to the red one it's 2. Okay. Last thing, and oh wait, 5 minutes. Yeah, I have time for this. Real. What question?
Yeah, what happened with when you do the integral at the end? What happened with the pi?
What? Oh, did I forget to put the pi in there? Oh, I forgot to put the pi. Thank you. It was here. It was sitting right out in the front. You didn't see it? I had put it right there in the front. Okay, so what if we do the same thing? This time we put our axis of rotation vertically, and let's call it x equals k, and we want to rotate around that. And our region goes sideways where our rectangle is horizontal instead of vertical. Same thing, isn't it? Except I'll have an outer and inner, which will be a distance that you'll have to look at. Your outer one is from there, and then your inner one is here. So integral c to d instead of a to b, pi, outer squared minus inner squared, d y. So you should be able to, on 7-2, you should be able to start 1 through 17 odd. So I really do hope you finished all this chapter 6 homework. 1 through 17 odd. That's out of 7.2. That's page 379. So here's what I recommend that you do by next class. Definitely try and knock out those 7-1 problems, and at least do one x-axis rotation and one y-axis rotation before we meet again. What we still need to do is, well, I don't know. We'll see how the next day goes. There's one more thing in this section that we have to cover. All right, one more thing. Have a good day. We'll see you on Wednesday.